Welcome to the deep dive. We are heading into some incredibly rich territory today for you.
We really are. I've been looking forward to this one.
Same here. So our mission today is to explore a very specific, highly clever programming workaround. But honestly, it's also a journey into the mind of a incredibly prolific polymathic creator.
Yeah, the context is just as important as the code here.
Exactly. So we are looking at a single source today. It's a blog post titled Notes on Haskell Programming Part 71, using Guard to handle nested ifs.
Part 71, just let that sink in for a second.
Right, Part 71. And it was written on March 2nd, 2026 by a creator named Ang.
And he runs the site kianmne.org.
That's the one. Okay, let's unpack this, because before we even touch the specific Haskell code...
The nested ifs.
Right, the nested ifs. Before we get to that, the context of who we are learning from entirely changes how we view the solution he presents.
It absolutely does. Understanding the author is crucial here. Right at the top of the site, Ang actually refers to his space as the journal of an old software plumber, night-long tinkering with free Libre and open-source software.
An old software plumber. I really appreciate that framing.
It's great, right?
Calling himself a software plumber sets a very specific tone.
What's fascinating here is how it immediately grounds the conversation. It strips away the academic pretension you often find in advanced computer science circles.
Especially around functional programming languages, they can get very dense.
Exactly. Very theoretical. But a plumber isn't dealing in pure abstract theory. A plumber deals with flow, with pressure, and with finding practical ways to route things from point A to point B without the pipes bursting.
Right. It's a highly practical, tinkering mindset.
Yeah.
And that completely drives this entire piece we're looking at.
Yeah, it's not a sterile textbook.
Not at all. And the volume of that tinkering is massive.
Yeah.
Looking at the archive of this blog, the consistency is just a major takeaway from it.
That's staggering.
He has been blogging since July of 2011. And to put some actual numbers to that, in 2025, Ang published 730 posts.
730.
Yeah. And in 2024, he published 732 posts.
Which averages out to 2 posts a day, consistently, for years.
It's mind-blowing. Even in just January of 2026 alone, he published 93 times.
And it's not just code either.
No, not at all. While we are looking at his 71st post on Haskell Programming, his project list includes this extensive series on gardening.
Which is up to part 824, by the way.
824. And he also writes about fish keeping.
Right, currently at part 2 of 3, and that includes these highly specific beta spawn logs.
Beta spawn logs, plus ongoing notes on typesetting, artificial intelligence, and meditation.
So we are learning from someone who views code as practical plumbing, but approaches learning with this relentless cross-disciplinary curiosity.
Exactly. So when someone who spends their mornings analyzing the complexities of plant growth and their evenings analyzing the complexities of Haskell syntax tells you they found a better way to organize a system, you pay attention.
You absolutely do. They understand organic growth and structural limits in a way most people just don't.
Which brings us to the specific structural limit Ang is tackling in this post. How to handle nested if statements in Haskell.
The nested ifs.
Right. But let's slow down there for a second,
Yeah.
because we need to establish why this is a unique problem in Haskell specifically.
Right.
I mean, most programming languages have if statements. You know, if a condition is met, do one thing. If not, do another.
It's the most basic building block of logic.
Exactly. So why is nesting them such a specific headache in Haskell that it requires a 71st blog post to discuss a workaround?
Well, to understand that, we have to briefly touch on what makes Haskell different. Haskell is a purely functional programming language.
Okay.
In a lot of common languages, say Python or Java, you can write imperative code. You can literally tell the computer, do this step, then change this variable, then do this next step.
Right, you're giving it a recipe.
Yeah. You can build a messy, deeply nested if statement, and inside that statement, you can just mutate data on the fly to get whatever result you want.
So imperative languages give you the freedom to be a little sloppy with your plumbing.
Precisely. You can patch things up as you go. But Haskell doesn't allow that kind of sloppiness.
Not at all.
In Haskell, variables are immutable. Once you set a value, it does not change.
It's locked in.
Locked in. You aren't giving the computer a list of steps to execute. You are defining declarative rules for how data flows and transforms from one state to another.
Okay, so because of that strictness, when you start nesting conditions, checking if this happens, then checking a second thing, then a third, the required syntax becomes incredibly rigid.
Very rich.
And Ang mentions his previous method for dealing with these nested conditions, which he calls tuple pattern matching.
Right.
Can you just define what a tuple actually is in this context?
Sure. Think of a tuple as a fixed-size ordered grouping of elements, usually wrapped in parentheses. So if you are checking 3 different variables, let's say weather, number of guests, and catering choices, a tuple groups them into one single package.
So you'd write it like parenthesis, weather, guests, food, close parenthesis.
Exactly. And in tuple pattern matching, Haskell looks at that whole package at once and tries to match it against a specific rule you've predefined.
I was trying to visualize how this works in practice for you, the listener, and I thought about organizing a complex event, like a giant outdoor wedding.
That's a great analogy.
Thanks. So if you use tuple pattern matching to plan this wedding, you are forced to write a specific, unique rule for every single permutation.
Right.
So your tuple might be rain, 50 guests, chicken. You have to write a block of code specifically for that exact combination. Then you need another block for rain, 50 guests, fish.
Yep.
Then rain, 50 guests, vegan.
And that is just the first 3 permutations. If you have 3 options for weather, 3 for guest count, and 3 for food, you're quickly writing out dozens of explicit rules.
But wait, if you have all those combinations in your system, don't you have to write them all out eventually anyway?
I think so, right.
Yeah. I mean, how does a computer know what to do if you don't explicitly tell it every possible scenario?
That is a great question, and it gets right to the heart of systems design. You actually don't need to explicitly define every single leaf on the tree, so to speak.
Okay.
Not if you can build a system that filters data sequentially. The problem with tuple pattern matching is that it demands explicit completeness for every combined state.
It wants the whole picture at once.
Exactly. So if you add just one more variable to your tuple, say, whether the band is playing indoors or outdoors,
Oh, wow.
yeah, the number of matching cases explodes exponentially. You go from dozens of rules to potentially over 100 just by adding that one single variable.
So nobody wants to manually map out 100 different wedding plans just because they hired a band.
Right. And as Ang notes in the blog, this adds unnecessary complexity to the code.
It really does.
In systems design, an elegant solution must scale. If adding a single variable causes your code permutations to skyrocket, your system becomes fragile.
And hard to read.
Very hard to read. It creates a massive amount of cognitive load for the programmer.
Let's talk about that term cognitive load, because that's important.
Cognitive load is essentially how much mental energy it takes for a human being to hold the structure of the system in their working memory.
Right.
A system that requires you to mentally juggle 54 different permutations is exhausting.
It's impossible to hold all that in your head.
And because of that, it becomes terrifyingly easy to make a mistake. You leave out one specific combination, and you inadvertently break the application.
Which means you are creating technical debt.
Yes.
Technical debt meaning you are writing code today that is going to be an absolute nightmare to fix or update tomorrow.
Exactly. The plumbing is just too tangled. The system needs a cleaner way to route the flow of logic.
Okay, here's where it gets really interesting. Ang introduces an alternative solution that avoids mapping out every single tuple permutation.
The workaround.
Yes, the workaround. He calls it the guard expression approach. And he compares this to an if-then-else chain that evaluates conditions sequentially, moving cleanly from top to bottom.
And the syntax he shares for this is visually very striking.
It is.
The guard is represented by a single pipe symbol on the keyboard, just the straight vertical line.
Right. And Ang uses a great metaphor here. He says the pipe symbol acts as a gatekeeper.
It's the perfect visualization. Instead of asking Haskell to look at a massive tuple and find the one exact match out of 100 combinations,
Which is exhausting.
you set up the sequential series of these vertical pipe gatekeepers. The logic just flows down the chain, hitting one gate at a time.
So imagine you were walking down a long hallway with a series of locked doors on your left.
Okay.
You walk up to the first door, the first gatekeeper. The system evaluates a single condition. Let's say it checks, is it raining?
Right.
If it returns false, the gatekeeper turns you away. But you don't crash the system.
Yeah.
And you don't even have to check the catering or the band yet. The logic is simply sent down to the next guard in the list.
You just keep walking.
Exactly. You walk to the next door. It evaluates you again. Is it sunny? False. Okay, drop down to the next one. It keeps dropping down, bouncing off these closed doors until it finally hits a condition that evaluates the JCOP. The gatekeeper opens the door, The logic executes, and you're done.
That top-to-bottom sequential flow drastically reduces the cognitive load.
It really simplifies things.
You are isolating decisions. You don't need to know the entire state of the universe anymore. You just need to know if you can pass the specific gate right in front of you.
But I do want to push back on this a little bit.
Sure.
Because as clean as that hallway of doors sounds,
Yeah.
Ang points out a very specific, quirky way that he actually has to initiate this sequence in Haskell.
The entry point.
Right. It's not as simple as just drawing a pipe symbol and starting. To unlock these guards, he combines them with a case of match.
Yes, that part is very interesting.
And the important part is what he is matching against. He uses empty parentheses, which is called a unit value. Why does he have to do that?
Well, this is where we run into the strictness of Haskell syntax again. The case of expression in Haskell is inherently designed to look at a piece of data, like a variable, and match it against patterns.
It expects to evaluate something.
Right. It wants to inspect the tuple. It wants data to examine.
Mm-hmm.
But Ang doesn't want Haskell to inspect the data at the top level. He wants to bypass that entirely and let the guards do the work sequentially below.
So he passed it empty parentheses, the unit value.
Yes. Ang explicitly describes this unit value as a dummy placeholder or value of no meaningful data.
So he is effectively tricking the structure.
He is. He's providing a blank slate.
Okay.
And then to make the match succeed, he uses a wildcard symbol, which in Haskell is just an underscore.
Right, the underscore.
The wildcard essentially says, I don't care what data is here, just accept it. And because the dummy unit value doesn't contain any specific data to contradict it, the wildcard automatically matches it.
So that effectively unlocks the guards that follow.
Exactly.
It's kind of like handing a bouncer a blank, featureless VIP card.
Yeah.
The bouncer is required by the rules of the building to check a card. You hand him a blank one, he uses a wildcard rule to accept it, and suddenly you are in the hallway where the real gatekeepers are.
That's a great way to look at it.
But honestly, that feels a bit messy.
It is a little messy.
If Haskell is this highly conceptual, beautifully strict functional language, why rely on a hack with dummy placeholders and wildcards just to get a clean list of conditions?
That is the eternal tension in systems design.
Yeah.
Sometimes the mathematically pure way to do something like exhaustive tuple pattern matching is completely impractical for human readability.
Right, it works perfectly for the machine, but the human hates it.
Exactly, and Ang recognizes this. He is actively choosing a slight structural hack at the entry point in order to gain a massive amount of readability and scalability down the line. It's a trade-off.
Ang also throws in a quick note that I found fascinating. He mentions that if you have an Elixir background, adding guards to function headers like this will feel very familiar.
Yes, Elixir. Elixir is another functional programming language, but it was built with a lot of practical, developer-friendly ergonomics in mind.
It's known for being a bit friendlier.
Very much so. In Elixir, using guards to filter logic before executing a function is a native, highly encouraged pattern.
So this is an example of cross-pollination.
Definitely.
Ang is taking a mental model that works beautifully in Elixir, this idea of clean, top-down gatekeepers, and he's figuring out how to implement it in Haskell, even if he has to use a dummy value to force the syntax to accept it.
Which is exactly the mindset of a polymathic tinkerer.
The software plumber at work.
Right. He understands the intent behind the design patterns of different tools, and he moves those concepts across domain boundaries. He's treating the languages as raw materials for his plumbing.
Let's look at the very end of that plumbing system, because we have this hallway of doors, these gatekeepers. You walk down, getting a false reading, dropping down, down, down.
You need a safety net.
You do. You need a guarantee that the data won't just fall off a cliff at the end of the hallway.
Yeah.
You need a final door that is absolutely guaranteed to open.
The catch-all condition. Every robust system needs one to prevent unhandled data from crashing the program.
And the way Ang handles this last guard is my absolute favorite detail from the entire source text.
Brilliant.
The very last gatekeeper uses the plain English word, otherwise.
If we connect this to the bigger picture, this is where the philosophy of language design really shines.
Yeah.
Ang explains that in the Haskell standard library, otherwise isn't some complex, deeply engineered functional operation.
Right.
It is simply a variable defined as an alias for true.
Let's make sure that's clear for everyone listening because it sounds almost too simple.
Mm-hmm.
Under the hood, the creators of Haskell literally just wrote code that says the word otherwise equals the Boolean value.
Mm.
True.
That's exactly it. That design decision was made purely to make the code more readable for human beings.
Wow.
When the programmer types the word otherwise, the computer's compiler simply sees the absolute truth value. True.
And because a guard opens its door anytime it evaluates to true,
It guarantees that this final gate will open.
catching absolutely any data that fell through all the previous false checks.
Exactly.
I just love that.
Yep.
Instead of writing, poke symbol, true arrow, do this final thing, which feels very rigid and robotic,
Right.
the programmer gets to write pipe symbol, otherwise arrow, do this final thing. It reads exactly like a human thought process.
It really does.
You are telling the system, check if it's raining, check if there are 50 guests, check if they want chicken.
Right.
Otherwise, just serve the default meal indoors.
It bridges the gap between how a machine processes binary logic and how a human being communicates intent. And again, it comes back to reducing cognitive load. You are hiding the mechanical plumbing behind a beautifully simple, readable facade.
So what does this all mean? Let's synthesize what we've covered today.
Good idea.
We've explored the mindset of a prolific tinkering software plumber named Ang.
Mm-hmm.
He takes on the problem of nested decisions in Haskell, a language that normally demands you map out every exhaustive permutation using tuple pattern matching.
Which creates massive technical debt.
Right. So to avoid the cognitive load of that exploding complexity, he borrows a mental model from Elixir.
The guard expression approach.
Yes. Setting up sequential pipe symbols to act as gatekeepers. He tricks the rigid syntax using a dummy unit value and a wildcard, creating a clean, top-to-bottom hallway of decisions instead of a sprawling labyrinth.
It is a massive improvement in managing logic flow.
But Ang remains incredibly pragmatic about it.
He does. He readily admits in the text that this guard approach is essentially a clever way to work around certain Haskell syntax limitations.
He knows it's a workaround.
Yeah, he's not pretending it's perfect.
He even acknowledges that some programmers might actually find this guard approach a bit cryptic.
And they might, because when you write out every single tuple permutation, it is undeniably obvious what is happening.
Even if it's messy.
Even if it's messy and hard to maintain. The guard approach requires the next programmer who looks at the code to understand the dummy value, the wildcard, and the sequential flow.
It requires them to know how the plumbing works behind the wall.
Exactly.
This raises an important question regarding how we approach the limitations in our own tools. Whether we are writing software, building physical structures, or even just designing organizational workflows.
Right.
When you hit a structural limitation, do you brute force your way through it, meticulously mapping out every messy permutation just because it's the obvious default way the tool wants you to work?
Or do you take a step back?
Exactly. Do you build clever top-to-bottom gatekeepers that might require a bit more abstract thought up front, but result in a system that can actually scale?
That tension between the obvious brute force method and the elegant, scalable abstraction is at the heart of all engineering.
It really is.
And Ang's journey isn't even over with this single post.
Oh, right.
He teases at the very end of the text that because of these syntax limitations, there are actually yet another 2 methods to explore in his next post.
The tinkering literally never stops.
Never.
The old software plumber is always looking for a better wrench. And I want to turn this around to you, the listener.
Yeah, how does this apply to you?
Because you don't need to be programming in Haskell to apply this kind of systems thinking.
Not at all.
Whether you are coding a new application, trying to optimize the workflows in your small business, tending to a massive garden, or, maintaining a specific tank of fish.
Just like Ang.
Just like Ang, you deal with complex, nested decisions every single day.
If this happens, then what?
And if that happens, then who takes responsibility? Take a look at the systems you've built to handle your daily life or your work. Are you manually handling every possible permutation? Are you carrying the cognitive load of 100 different conditional rules in your head?
That sounds exhausting.
It is. How do you design your systems to route those decisions sequentially so you don't feel totally overwhelmed by technical debt and unnecessary complexity?
That is the core takeaway regarding systems design right there.
Mm-hmm.
And I want to leave you with one final thought to mull over as you go about the rest of your day.
Okay.
It builds entirely on that beautiful concept of the otherwise alias we talked about.
Oh, I love this part.
Think about the fact that the creators of a highly conceptual, mathematically rigorous programming language went out of their way to specifically define the word otherwise just to serve as a human-readable alias for absolute truth.
That's so cool.
It does nothing mathematically different than just writing true. It exists solely for the benefit of the human mind reading it later. Look around your own life. What are the complex systems, the unwritten rules, or the daily routines in your workplace or your household that are technically functioning fine, but desperately need a human-readable alias?
Hmm.
What convoluted processes do you oversee that need a simple translation so that the next person who comes along can look at the system and easily understand exactly what intent lies behind the plumbing?
Making the complex human readable. We could definitely all use a little more of that.
Absolutely.
Thank you so much for joining us on this deep dive into the archives of an incredible tinkerer. Keep exploring, keep questioning, and we'll catch you next time.